So last week we introduced chemical kinetics. I went through like the first 5 slides. We're going to go through these first 5 slides again, right? Because I don't know if you remember everything I said last week, but it's important for you to know these definitions before we actually jump into the math. So let's go through this real quick, and it's going to be a good time. And then afterwards, when you go to discussion, you will be working problems with Ms. Dickens based on this lecture, right? So make sure you take notes because I'm teaching you how to do these kinetics problems now, and you'll be using that in an hour and a half in discussion. Okay. So again, chemical kinetics. We'll repeat what I said last time. It's the speed at which a reaction takes place. That's called the reaction rate, right? And so when we study these reaction rates, that's called chemical kinetics. And a step-by-step view of the change of the reactants to the products is called a mechanism, right? So when you're looking at two reactants and they come together to make some kind of product, or they break apart to make a different product, right? The actual process of them doing that, changing into a product is called the mechanism. And when you get to organic chemistry, you're going to do a lot of mechanisms, right? But we're going to focus mostly on the reaction rate and the chemical kinetics in this lecture, okay? So, like I spoke of last week, factors that affect reaction rates are things like the physical state of the reactants, right? So, if you have something that's solid, right, and you have another solid thing, and you just throw them together, are they going to react? Not really, because it's a solid. But if you have two liquids and you throw them together and they want to, they will react, right? Because the state of the reactants do make a difference. Okay. What we'll really focus on today is reactant concentrations, right? Reactant concentrations will also affect the rate of reaction. You can, for example, double the rate of reaction by doubling the reactants, for example, right? Which kind of makes sense. But we'll dive deep into that today, and we'll dive deep into it on Wednesday too, right? Of course, reaction temperature also increases the rate of reactants. The rate of reactions, and that makes sense too because if you're heating something up, it's more likely to have collisions, right? The molecules uh, vibrate faster, they fly around faster, and when they crash into another molecule, that can create a reaction, right? So that's the premise for reaction temperature, and then the presence of a catalyst. I've talked about that already before, where you can add something to the reaction, right? And it will change the mechanism of the reaction, and then the reaction will go faster, but you can get the catalyst right back out again, right? And the catalyst doesn't get affected by it. Okay, so that's a catalyst. So in fact, the vast majority of the reactions that happen in your body, like in metabolism and in immunology and all that stuff, right? Those are all based on biological catalysts called enzymes, right? So your first question is this: which of the following affects reaction rates? Which of the following affects reaction rates? All right, let's see how people are doing. Got one response so far. Whoever that was, they did it right. Good job. So we have 10 people in here. Oh, I wonder where Kimberly and Aubrey are. I just talked to Aubrey earlier. Weird. 7, 8 people. 2 more people, please. This question should actually be familiar because we did this question last week, but I'm going through the PowerPoint again. So, still waiting for 2 people. Still waiting for 2 people. Unless I miscounted. I did miscount. There's only 9 of you in here. There we go. 1 person. So, as I alluded to before, good job. Everyone got that right. All those are types of catalysts, right? All these are not type of catalysts. Sorry. All these are things that can affect the reaction rate. Okay. So the next few slides are going to be just going through each one of those individually. I pretty much did it already on that first slide, but just as a quick reminder, because I'm going to ask you questions about this, right? The more readily a reactant collides, the more rapidly they react. Just like I was talking before with things that are solid, you throw two bookcases together, they're not going to react to make something new, right? But if you have two liquids or gases and they collide with each other, the molecules actually collide with each other, then they will react more rapidly, right? Homogeneous reactions, all gases, liquids are often faster. I just said that, right? And heterogeneous reactions involve solids are lower, or slower, right? Faster. The faster these reactions occur, if the surface area is increased, and a fine powder will react more than a pellet or a tablet, right? So again, the reason why it's a fine powder is because if there's more surface area around the actual hard solid material, there's more collisions that can occur that can actually have the reaction. So the thing to take home from this is that things are liquids and solids, liquids and gases. They often react much faster than we have a solid and a liquid. So we also have reaction concentrations right here. If you look at this picture, which I showed you last week too already, this is just some steel wool right there on a Bunsen burner, right? And it glows red hot when you put it on a Bunsen burner. But when you put that same steel wool inside of a beaker or a flask rather, and you pump it full of oxygen, it almost explodes, right? Because the reaction is much faster when the concentration of oxygen is much higher, right? Because remember, out in the atmosphere, there's only like 20%, oxygen, 25% oxygen. But inside this flask, you can pump it full of oxygen, and then you'll have a little bit of an explosion happen because it reacts much faster. I wanted to do that in class, but they wouldn't let me. They said it was too dangerous. So it's too bad. So another thing again, so I said this already before, the temperature also increases reaction rates because you get more collisions, right? Increasing the number of collisions between the molecules. That increases reaction rates because you heat something up and the molecules just bounce around much faster. And last, and certainly not the least, the presence of catalysts, right? A catalyst will affect, this is the definition that you need to know, the catalyst will affect the rate without being in the overall balance equation, which means you can throw in a catalyst and then it'll do its thing to make the reaction faster, and then you can pull it back out again. Nothing changes with the balanced equation, okay? How do you do it is by changing the mechanism of the actual reaction, and then catalysts are critical in many biological reactions, and they absolutely are. If you didn't have any biological catalysts like enzymes, you'd be dead. You would be absolutely dead, okay? Next question, which of the following is not true about a catalyst? Catalysts affect rate by being a part of the overall balance equation. Catalysts affect the kind of collision based on changing the mechanism. Catalysts are critical in many biological reactions. Or D, all of the above are true. All right. Read the question carefully. Read the question carefully and read the answers carefully. Read the question carefully. It's okay if you got it wrong. If you know you got it wrong just now, then I'm fine with that. I might laugh at you later when I'm going through the attendance, but but it's fine. I'm glad you realized that you made a mistake. Right? Read the question very carefully. All right, we got 8 responses. I need one more. I'm holding on. Cool. All right, so we literally had half and half here, which is fine. It's still Monday. It's early. Well, to me, it's early because I woke up like 10 minutes ago, but maybe you guys woke up earlier than I did. The vast majority of you said A, right? Well, there can't be half and half because there's an odd number of people today, but not the vast majority, but the majority. There we go. Maybe it's called the plurality. The plurality of you, right? Didn't answer the correct answer there. It is answer A, because remember the definition of, and this is the definition you need to know for an exam, right? Is that catalysts affect the rate by not being a part of the overall reaction, okay? By not being a part of the overall reaction. So that's why A is not true, because that says it's being a part of it. It's supposed to be not a part of it, okay? So moving forward, talking about reaction rates, the rate is a change in concentration over a period of time. And you actually saw this when you did the experiment last Wednesday, when you put the stuff into the Spec 20 and you saw the numbers going down. Remember that? Right? That was actually a change in the concentration of crystal violet. Okay? Because it reacted with the hydrogen peroxide, the crystal violet was changing to something else, and that's why the numbers were going down. Does that make sense? Right? So we generally use this equation here, where we have the change, this triangle right here, which is a delta, is a change, and then the brackets right here are concentration, right? And then divided by the change in time, okay? So, just to say one more time, just to be reiterating here, the rate is equal to the change in the concentrations of a reactant or the product or anything over the change in time. Okay, so delta means change, brackets means concentration, T's mean time, right? So the average rate is measured in the average rate, the instantaneous rate, or the initial rate. Those are the three types that we measure, okay? The instantaneous rate, the average rate, and the initial rate. So let's apply this then to a reaction. Okay, so let's apply this to a reaction. So we have here this molecule, I don't know what this is, 4, so that would be butane, right? So yeah, maybe this is called butane chloride, or chlorobutane, right? Chlorobutane right here, the C4H9Cl. That's not so important what the name of it is, right? But you're going to be combining that in a reaction with water, and what you get out of it is butanol. Wait, that's not even butanol. Is that butanol? Yes, that is butanol. Yeah, okay. You'll get butanol and hydrochloric acid, right? It's almost like this is what they do, the reaction that they use to actually make hydrochloric acid. So that's pretty cool, right? So you get butanol and hydrochloric acid, right? Both of them are AQ. What does that mean? Exactly, aqueous. They're in solution, right? And so the rate of the reaction is measured using the concentration of change of reactant over the product or a product over time. So here in this example, we're going to use one reactant here, right? That reactant will be chlorobutane or butane chloride, chlorobutane, whatever, same thing, right? And so since we're looking at the concentration of the chlorobutane, we're going to put the chlorobutane's formula inside of the concentration brackets, right? And so the equation then now is the rate, right? The rate equals negative change in chlorobutane over change in time. Can anyone tell me why we have a negative there instead of just regular old change? Well, if you think about it, chlorobutane is being changed into butanol, right? So we're losing chlorobutane as time passes. Does that make sense? And since we're losing chlorobutane as time passes, that's why it's a negative number, right? So if we were to put a product there instead, like hydrochloric acid or something there, or butanol there instead, it would be what? A positive number, because we're getting more of those. Does that make sense? Right? So, yes, ma'am. So the slide where it has the equation for reaction rate, yeah. The delta with the brackets, is it divided by the delta times T? Yes. Yes, that is a division sign right there. Yep. But yeah, so if you were to put the products, one of the products in the concentration brackets, it would be positive, right? Because you're making products. But if you put one of the reactants into the concentration brackets, it would be negative because you're losing reactants as time passes. Does that make sense? So that's why it's negative right there, okay? That'll come up later. All right, I'll give you a chance to write that down. And while you're writing that down, here's your next question. Keeping you involved today. I keep you involved every day, don't I? You guys should be excited. I'll be the one teaching your lab this week, right? Because Miss Dickens was going to cover for me if I was gone. So, and it's going to be an easy one. It's going to be all on computer, so you don't have to, get dressed up for lab that day. You wear shorts and tank tops or whatever it is you crazy kids wear these days. I was going to say you don't have to wear pants to class, but that sounded weird, so I refrained from saying that. Except I just said it just now, so. All right, let's see how people did on that question. Everybody's responded. Good job. Woohoo! Everybody got that one right. The delta means the change, right? Which is A. Good job. Yes, ma'am.
What is time in
Seconds.
seconds?
Yes, ma'am. Some reactions take longer than other reactions, though, so it could be milliseconds or shorter. But generally, when we're talking about like using the SI system, right, time is always going to be in seconds. All right, so I want to show you the rate of this reaction right here. It's kind of interesting here. If I can get to that slide, there we go. All right. So, what happened? Okay. So here's the reaction data for butanol chloride. No, what did I call this? Chlorobutane with water, right? So here we have time. It's in seconds, right? And you have 0 seconds here. You're ending with 10,000 seconds there, right? Here on this, at the top here, we have the concentration of chlorobutane. And then over here, we have the rate of this reaction. And notice that the rate of this reaction, the units of this rate of reaction is what? It's not meters per second, is it? It's like molarity, right? Molar per second, right? So that's the change in concentration over time, right? Big M is always molarity. And what I want you to notice here is that as time passes, right, the concentration of chlorobutane gets smaller, right? Here at 50 seconds, it's 0.905. At 100 seconds, it's 0.802, 820. At 150 seconds, it's 0.074, and so on. As you see, it is actually going down because over time, you're going to change all of that chlorobutane into what? Butanol, right? And hydrochloric acid. The other thing to notice here too is that notice how at the very beginning of the reaction, the rate is faster, but then by the time you get to the end of the reaction, the rate is like a fourth of it, right? So two things to notice in this chart here, okay? As time passes, the concentration of chlorobutane decreases, and as time passes, the average rate of the reaction decreases, right? Those are two things to notice there in this chart. I told everybody last week that I'm like totally winging this and I have no idea what I'm talking about. And I literally just, I don't know the stuff like ahead of time. I just like look at the slide and tell you what I see. So, so otherwise I'd have like notes and I have like a script, and everything. But no, I'm winging it just like you guys are. So makes you feel reassured, doesn't it?
Okay, so let's talk about graphing the data from the previous slide. When we graph the data from the previous slide, we can actually determine some very interesting values, one of which is called the instantaneous rate. The instantaneous rate is basically the rate of the reaction at any given point in time. Okay. At time 0, though, we call it the initial rate, and it's important and special to us because at time 0, generally the rate is at its fastest because as you can see from over this graph, you can see on this graph, as the reaction progresses, the reaction rate actually slows down, right? The reaction rate decreases. So if a chemist wanted to be able to see what the reaction's rate actually is, he or she wants to see it at its fastest, they'd want to get the instantaneous rate at the at point zero, right? Right when we first start the reaction, okay? And so we can actually very easily figure out what the instantaneous rate is at point zero, or the initial rate, right? Right here on this graph, it even tells you that the instantaneous rate at time at any given time is equal to the slope of the tangent at that time, right? Equal to the slope of the tangent at that time, right? So let's use that to figure out the initial rate or the instantaneous rate at zero uh, here, okay? So here is the rate, here's zero right here, okay? And here's the concentration of the reactants at time zero, okay? So we want to be able to figure out the instantaneous rate or the initial rate right there at that point, right there that I'm putting that arrow on, okay? And the way we do that, based on the statement right here that I just underlined, the way we do that is by taking the slope of the tangent to the dot or the data point at time zero and concentration 0.1, okay? So, bring over a ruler, and I have one on, oops, didn't mean to change the screen there. Let me go back. Go back. There we go. So I have a ruler here, and I can put the ruler on top of my screen, and then I can draw a very straight line that will represent the tangent of that line, okay? The tangent of the line at that point, right? Okay? And so when I do that, what I need to find now then is the slope of this line, okay? The slope of that line, because the slope of that line equals the instantaneous rate, right? At that point, okay? And really, you could actually go up and down the line of the data, right? This line that's made by the data here. Pick any one of those points on that line, that curved line, right? As long as you use the slope of the tangent of that point on that line. You can use any of those lines, and you should come up with a reasonable number, right? But since we want the slope at since we want the slope at the time zero, or the initial rate, right? We're going to use this line and this slope right here, and at that point, okay? So if you recall back when we were talking about graphing and very early on in the semester, right? The slope of a line is m equals the change in y over the change in x, right? And then also, if you recall back, maybe 2 or 3 slides ago, I can't remember, right? The rate actually equals the negative change in the concentration of the reactants, right? So in this case, it's the the chlorobutane. So that's C4H9Cl, all divided by the change in time. Okay, all divided by the change in time. I want you to also notice here that this term is negative right here. It's definitely negative, and the reason why it's negative is because we're losing reactants over time, right? If you were talking about the products being made, right, the butanol or the HCl, then it would be a positive. But we're looking for the instantaneous rate of the reaction as the chlorobutane is being lost, right? Is being converted over to something else. Okay. So quite simply, then we'll try to figure out to get this rate, right? We need the change in y over the change in x. So in this case, y is the change in concentration, right? So I will move over to the left over here where I have a little bit of room, and I can write the equation out as the rate equals, right, at the negative, and I'll go ahead and put the divide sign there so I know what's above and what's below. And we're going to just choose this line right here for the y, right there, and we'll get the slope at that tangent line right there, right, that change right there. So our initial here is 0.1, and our final here is 0.06 molar, right? So on the top, we'll put 0.6, right, minus 0.1, right? And then at the bottom, it's a change in time, right? It's a change in time. So there, we'll estimate here a little bit. This tangent line comes over here a little bit, right here. We'll take it all the way down to the x-axis. And I'm thinking that is about 210 seconds. So the final first, which is 210 minus 0 seconds, because we were at time 0 at the beginning, right? And all we have to do now is do this multiplication here, or sorry, this division here, right? And we can solve for the instantaneous rate at time 0, right? And I'll take this down here so I can write it out more clearly. We get the answer to be then an instantaneous rate of 1.9 times 10 to the negative 4 molar per second, okay? By the way, that is the unit molar per second, okay? And so the interesting thing about that is that we ended up with a positive sign here, even though we had a negative sign here in the equation, right? You just got to remember your order of operations here. And so since this top term right here actually becomes negative, a negative times a negative makes a positive, and that's why we have a positive rate. That being said, though, the graph does show that the rate is slowing down, right, and going in downward direction as as the reaction progresses. So the other interesting thing to notice too is that when we just did this calculation right here and got this particular answer, and I don't know why I didn't draw a square around the unit 2 because it goes with it, right? We can go back to the data from the previous slide and see if we match up, right? And if you notice right here on the slide, on the previous slide, right, here's time 0 right there, and look what the rate was. It's exactly what we calculated, 1.9 times 10 to the negative 4, right? Molars per second. Never forget the units, right? So that's how we do that.
Okay, so I actually talked about this a second ago, okay? But we'll rehash it here again because it's important. Okay. As you said, rates are followed using a reactant or a product, right? So does this product give the same rate? Does this give the same rate for each reactant and product? Well, the rate is actually dependent on stoichiometry. Okay, it's dependent on stoichiometry, and if we use I keep on forgetting its name, chlorobutane, and compared to the production of butanol, right? The thing that would change is the sign, right? And I said this a second ago, right? We have a decrease in chlorobutane, and that's why the sign is negative, right? But when we have an increase in butanol, then the sign is positive, right? The sign is positive because as the reaction increases, butanol's concentration goes up, so it's positive. But as the reaction progresses, the concentration of chlorobutane goes down, and that's why one of them is negative. This is always the reactant, and the one that's a product, right, is always going to be positive, right? So I could put here what? I could also change that to say HCl. It would still be the same, right? Because that HCl was a product too. Or I could change this one to say water. That was a reactant. Does that make sense? Right? Okay, good stuff. Good stuff. Yes, absolutely, absolutely. And I'm about to alliterate. No, elaborate. Elaborate on this statement here. Rate is dependent on stoichiometry in just 1 second. Letting people get a chance to write down what I just said. Sorry, this is like some of my favorite stuff. So, and like it really is some of my favorite stuff. But luckily, there's a video. Luckily, I'm recording, right? Luckily, I'm recording, so you can go through and listen to it again. Okay. Yes, when you put a reactant into the rate equation, it's always going to be negative. But when you put a product into the rate equation, it will always be positive. Yeah. I mean, I usually get really excited and go fast on other things too, but this is some of my favorite stuff. The rate equation? The rate equation? And it's called the rate equation because the rate equals something, right? That's why it's called the rate equation. Yes, ma'am. You have a question, don't you? Yes, it was. That was literally a quiz question on the lab. That was a quiz question on the lab. I'm so glad you noticed. All right. So I'm going to go on a little bit here.
So I was just saying how the rate is dependent on stoichiometry, right? And what did I mean by that? Well, what I mean by that is the fact that what if you don't have a one-to-one ratio, right? In our previous example, we were doing the chlorobutane with water, and our results were a, uh, butanol and a hydrochloric acid, right? But when we wrote that reaction out, the balanced chemical equation was a one-to-one ratio for all the reactants and all the products, right? So what do we do when we have a reaction when it's not a one-to-one ratio, like this one and this one here, where we have uh, ozone decomposing into oxygen, right? And the ratio is actually 2 to 3, right? 2 to 3. What do we do with that? Well, there is this general rate equation, right? And it's based on this general equation of a chemical reaction, where if you have little a is a coefficient to big A, which is a reactant, right? Plus little b is a coefficient to big B, the reactant. That turns into little c, big C product, plus little d, big D product, right? And knowing that that's just a general chemical equation for any kind of reaction, right? We then know that we can do this, right? We can make a general rate equation like this one right here. So the rate equals, right? For the reactants, it's always going to be negative. So negative 1 over little a times the change in the concentration of big A over the change in time. And that also equals the negative 1 over little b times the change in concentration of big B, right, divided by the change in time, right? You can do that on the product side as well. The rate equals, since it's a product this time, though, it's not going to be negative, right? So it's going to be 1 over little c times the change in concentration of big C, the product, right, divided by the change in time. And that equals 1 over little d, and again, it's positive this time because it's a product, times the change in the concentration of big D over the change in D. I mean, the change in T, or time, right? So as you can see here, here's our big A, right? And here's our, what represents big A in this equation is the O3, or the ozone, right? And in this particular equation, we only have one reactant, so we don't even have to worry about uh, the B term, okay? And then for this reaction here, C, little c, right, is 3, and big C is O2, or oxygen, right? So now we have all we need to write out the rate equation, right? We have all we need to do, right? Because 2, again, is little a, right there. Ozone is big A, right there, the concentration big A, right? We go ahead and not worry about, whoops, I'm sorry. We go ahead and not worry about the, we go ahead and not worry about the B term, right? Because we don't have a second reactant. And then the same thing is also true over here with the products. We do have a single product here, which is oxygen, right? But we don't really have a second product, so we can just, not worry about that second product either, okay? And so what happens here is that since this is the 2 for little a, and little a is now down here in that equation, right? this is what you get right here, -1/2, right? The 2 becomes the denominator, right? Because the little a became the denominator in this rate equation that we have here, this general rate equation, okay? And then as for the 3 here, it became the denominator down here in the products of the rate equation, right? Because if you look over here, little c is under 1 right there, right? And so that's how we write our rate equation, okay? These two terms right here can actually be all combined into one. I just split them up there because I ran out of room. But you can write it as the rate equals the negative of 1 over little a times the concentration, or the change in the concentration of big A, right, divided by little t, which is time. And then that equals negative 1 over B times the change in concentration of B over the change in time, right? And remember that both of these right here are reactants, and that's why they're negative. But then we come over here to the products now, and it's positive, so now you can just write equals 1 over little c times the change in big C's concentration over the change in time. And then the same thing is then also true of D, 1 over little d times the change in concentration in big D all over the change in time, like so, right? And so that's how we figure out how we write the equation with the coefficients, all right? Because remember, when I'm talking about stoichiometry, I'm talking about the coefficients that are in front of each of the reactants or products, right? And whenever the stoichiometry is not 1-to-1 or the coefficients are not 1-to-1, this is what we have to use right here to figure out what our rate equation is going to be, right? Interesting stuff.
Here is your next question. Don't worry, it's an easy one. What is the mathematical rate dependent on? Temperature, concentration, stoichiometry, or all the above? This is such a good time. I hope you guys are enjoying this just like I am. I really hope you guys are enjoying this like I am. I mean, I'd venture to say this is one of my best lectures ever because I'm using the board, I'm using the PowerPoint. It's like hybrid type of style. It's a great time. I'm sure you're all thinking in your heads, well, I'm glad he's having a good time. At least somebody in the room is having a good time. It's not that bad, I promise. Especially when you listen to the video over and over and over again, like at least 20 times. It's great. If anything, it'll help you fall asleep at night. Oh, that Dr. No talking math. It makes me so tired. All right, so looking at the answers. Good job. The vast majority of you got that one right there. The answer is, in fact, stoichiometry, right? Stoichiometry is what we depend the mathematical rate on because stoichiometry is what? The coefficients, right? And those coefficients literally go straight into um, the rate equation, right? They go straight into the rate equation. And I don't know if you remember me saying this a second ago. I put a big T there a second ago. Remember? It's like, wait, it can't be big T. The reason why is because big T stands for what? Temperature, not time, right? Little t is time, big T is temperature. And so that's why all these have the change in little t's. Okay? All right then. We're doing so well. We're making we're not making super good time, but that's all right. I planned on spending the next 3 days on this, so it's all good. Oh, I forgot to change it back over again. Okay, so determining the concentration effect on the rate. How do we determine what effect the concentration of each reactant has on the rate, right? So a second ago, we were talking about the coefficients having the effect. Now we're actually going to talk about the concentrations having an effect, okay? We keep every concentration constant except for one reactant to see what happens to the rate. Then we change to a different reactant, and we'll do this until we have seen how each reactant affects the rate. And I'm going to show you what that means in just a second. Yeah, no problem. Yeah, no problem. No problemo. I am here to serve you guys. You pay me very well to sit here and talk. So I serve you guys.
I went to the bookstore today
Uh
to
huh.
buy a charger.
Uh huh.
It was $25, and then
Oh my God. Go to Amazon and buy it for like $1.
well, I needed it like right now. And then I went. It wasn't the right charger. I
Of course
tried
not.
it to try and make it work, but it wasn't the right charger. So I went to the Dollar Tree up there,
Yeah.
and it was only $6 there.
Well, for one thing, I think that's weird that Dollar Tree is selling things for more than $1. But number two, it is still cheaper than buying it at the bookstore.
Like I was shook.
I was too when I went to buy my very first Wesleyan T-shirt, and it was like $40. I'm like, holy crap, really?
Wait, it was $20.
Yeah, right.
A charger is half the price of a sweatshirt. That is ridiculous, y'all. That is ridiculous.
At least you think, at least like there's like licensing agreements, and that's why it makes the sweatshirts more expensive. But like the charger though, that's like generic from China. That should be like $1. Oh, I should go get some. Yeah, the one it's right across from President Slaybox's office.
Sweatshirts for $40.
Dang.
That was 2 weeks ago.
Must be the wrong season for getting certain things, I guess.
If you shop online too,
It's cheaper.
it's cheaper. Yeah.
Okay, so we're actually getting close to the end of class. No. I was gonna say that this stuff is a little complicated. So, do you want to go over anything, talk about anything before you go into discussion to do the problems, or do you want to continue until the time ends? We have like 7 minutes. To what?
Are you going to go over what you're about to teach in discussion?
What
Like
questions?
this right here.
Yeah, I'm gonna go over that. I can if you want me to.
Don't you think, are we doing that in discussion? What you're about to
Quite possibly. I don't remember. Quite possibly. So I better go over it.
Our homework is due tonight, right?
Which homework?
Homework 6.
Yes, it is due tonight. Everything is always due. Yeah, assignment 6.
Everything is always due what?
Everything's always due at the end of the day of the next class period that was assigned.
Okay.
That way you have time to ask me questions about it before it's due. Right? Okay, so just to I guess I'll try to finish this part. That way you're not like lost in discussion later, okay? As I was saying in this previous slide right here, right? What we do to figure out what the concentration has on the rate, how we figure that out is that we change one of the reactants of the reaction to see how it affects the rate, and then we change the other of the reactants to see how it affects the rate. And the way we do that is by doing this, okay? So now I have a reaction, right, in which I'm combining, right, ammonia with nitrite, okay? And so for experiments 1 through 3, right here, experiment number 1 through 3, what's happening here is that I'm doubling the concentration of ammonia, right? But I'm keeping the concentration of nitrite the same, okay? To see how that affects the rate of the reaction. And then for experiments 4 through 6, right? 4 through 6, I'm keeping the concentration of ammonia the same, but then I double the concentration of the nitrite. Does that make sense so far? Right? And I want you to see what's going on here. When I double the concentration of ammonia and not the nitrite, right? The rate actually doubles, right? I start out with around 5, I get to around 10, and I get to around 20, right? The rate doubles. But then when I change over to where I'm keeping ammonia the same and doubling the concentration of nitrite, the same thing happens again. The rate starts out at 10, so around 10, doubles to 20, around 20, and then doubles again to 40, right? So whether I double the concentration of nitrite or double the concentration of ammonia, right, the rate doubles, right? So the thing you can say is this. When I double the concentration of the reactants, I double the rate of the reaction. Does that make sense? Okay, that's like the general thing you can say, which is actually on the next slide. I just wanted to say it ahead of time. Okay, so for experiments 1 through 3, right, the concentration of nitrite stayed the same. So any of the changes in the reaction is actually because of the change in ammonia. Reaction 1 through 3 was the one where I doubled the concentration of ammonia, right? Every time. So you can say, for example, this here, where the rate 1 of ammonia, right, divided by, the rate of the second reaction, right here, right? Remember there are 1 through 3. I wish this was on the same slide, right? So remember it's reactions 1 through 3, right? 1 through 3, okay? So here on this equation, what it is that this is the rate from reaction 2, and this is the rate from reaction 1, right? Which equals the concentration of ammonia in reaction 1 divided by the concentration in reaction 1. I'm sorry, that's reaction 2. Let me say that one more time. Rate of reaction 2 over rate in reaction 1 equals concentration of ammonia in reaction 2 over the concentration in reaction 1. Okay, does that make sense? And when you take those numbers from over here, from reaction 1 and 2, right, and you plug them in, what you get is 2 equals 2, right? The concentration, this number here is 2, right? And then for the rates, it's also 2. So 2 equals 2, right? And so what that means is that the order is 1. The reaction order is 1, okay? Now you may have noticed that there's an X there. We'll talk about that later. But this X here means that, say instead of going reaction order is 1, right? Usually that 1 goes right there where the X is. But say instead of the rate doubling, it quadruples every time, right? Then instead of this order being 1, it actually would be what? 2, because 2 times 2 is quadrupling, is 4. Does that make sense? Right? So since you see that the rate divided by the rate here for the first and second reaction equals 2, and the concentration of ammonia divided by the concentration of ammonia is also 2, the order of the reaction is order 1, right? Does that make sense? I know this is crazy stuff. So this is your next question right here. With respect to ammonia, as the reactant, oh, I forgot to put the word double there. As the reactant doubles, right, insert doubles in there. As the reactant doubles, what happens to the rate? I haven't actually combined everybody yet, but it's pretty close actually. Sorry, somehow I messed up that question. I forgot to put in. With respect to concentration, as the reactant's concentration doubles, what happens to the rate? Oh, I did say that at the bottom there. Yeah, what happens to the rate when the concentration doubles of ammonia? Okay. Okay. Oh my gosh, good job, everyone. Good job. Oh, you haven't put in yours yet? Okay. No problem. All right. Good job. Again, the vast majority of you got this correct because I said it like 5 times, right? For this reaction with ammonia and nitrite, when we doubled the concentration of ammonia, we also doubled the rate, right? But as you can see from my uh, options, right? You can see from my options, you can do reactions where the rate stays the same, or it can triple, or it can quadruple, right? Those are possible, and you'll see those later. Okay. Let's do the same thing again now, but instead of a second ago we saw the numbers for changing ammonia. Now let's look at the numbers for changing nitrite, doubling nitrite. Same thing again here, right? Here, ammonia stays constant, so any change is due to only the nitrite concentration. And here, when we put the rate of nitrite over the rate of nitrite divided by the concentration of nitrite and the concentration of nitrite from reactions 3 and 4, we get the same thing again, where it's 2 equals 2. You divide this by that, it's 2. You divide by that, it's also 2. So that is also order 1, right? So as the concentration of nitrite doubles, what else doubles? The rate doubles, right? So you should be hearing like a pattern now, right? Whenever the rate doubles, because the concentration doubles, the order is 1, right? Whenever the concentration doubles and the rate is quadruple, the order is 2. Make sense? Right? And you'll see more examples of that in a second. Okay? All right. This is going to be your last question for today, because you need to go over to the other classroom. What is the order of this reaction with respect to nitrite? This stuff is so fun. Like, once you really get it, it's so fun. We've got 7 people responded already. Still waiting for 2 more. That's good enough. 8 people responded. Good job. Everyone got that one right. In fact, when you double the concentration of nitrite, you get double the rate. All right. So head over to discussion over there, and I'll post this video on Blackboard for you so you can watch it, and we'll continue discussion on kinetics on Wednesday. Have a great day, everybody.